All right, so we're going to do example 6-6, just part A of it. What we have is an AC source connected to a capacitor. So it's going to look like this. Here's my capacitor. Here are some wires connected to this source with a voltage. The AC source has amplitude V0 and angular frequency omega. So we're going to call that little VC is going to be equal to V0 sine of omega t. Remember that when we use omega like that, it's equal to 2 pi times the frequency because it's an angular frequency. And that source is connected, again, across the parallel plate capacitor. Part A is to verify that the displacement current is the same as the conduction current. How do we do that? We find the displacement current and the conduction current, and then we compare them and find out if they're the same. So, where is their displacement current? If you remember, the displacement current density is partial d partial t. So it's the time derivative of the electric flux density. Now, in the wires, d is going to be 0 because it's a conductor and all the fields are 0 in the conductor. In the space between the capacitor plates, d is not going to be 0. So that's where we're going to find out what the displacement current is. How much displacement current is there? We're going to find the displacement current, which I'm going to call little I sub d. We're going to kind of do this in parallel in time domain and in phasor domain. So lowercase, that's lowercase means it's in time domain, and uppercase means it's in phasor domain. So if I were to write capital I sub d, that also refers to displacement current, but it's a phasor. Make sense? All right. So how exactly do we find the displacement current density? The total displacement current. If we know the displacement current density, we have to choose a surface and integrate the amount of displacement current density that passes through that surface. So we're doing a flux integral. So if you take a look, this is a close-up on the capacitor. We're going to have a D field that is perpendicular to the plates. And what we're going to do is choose a surface of integration that is parallel to the plates right between it like that. Because of this, when we take the dot product of the surface normal with the displacement, with the displacement current density, we're just going to get the magnitude of the displacement current density. So I'm going to drop the vector notation on top of the D. Hopefully nobody minds too much. You all forget the vectors on top anyway, and you shouldn't. So this is going to be my surface S. Those little vector arrows that I drew in there are D. So my displacement current, I sub D, is going to be equal to the integral over the surface S, partial d, partial t dot ds, or once we evaluate that, since d is constant over the area of the capacitors, and d dot ds just equals magnitude d times ds, I'm going to drop those magnitude bars, and I'm just going to write this as partial d partial t times the area of the capacitors A. All right. But what exactly is D? We never actually worked that out. Luckily, we know a lot about capacitors. So let's go back up to here. Remember that inside the capacitors, there's probably a dielectric, and the relationship between the electric flux density and the electric field is that D is equal to epsilon E. So we have that. And if there's a voltage across the capacitor, which there is, the electric field, well, the electric field magnitude, but we already know its direction. We have electric field magnitude is going to be equal to the voltage across the capacitor divided by the distance between the plates. And let me just add some notation here. That is the distance between the plates, and the plate area is A. All right, so that means that down here, well, I'm going to make another line so we have enough room for all our math. I sub d, if we substitute in what we now know about the relationships between D and E and VC, what we have is that I sub d is A epsilon over D. Oh, hey, that's the formula for capacitance for a parallel plate capacitor. Times the time derivative of VC. Now, if you remember that we wrote VC is a sinusoid, what that actually works out to is epsilon A over D times V naught times the time derivative of sine omega t. When we do that, we get little id is equal to epsilon A over D V naught omega cosine omega t. There we go. That's ID. That was in time domain. If we were doing this in phasor domain, let's go back up to that line where we're evaluating the integral and see what happens when we do it in phasor domain instead. If we do that, then capital I sub d is equal to surface integral partial d partial t ds. Now that time derivative, because we're dealing with phasors, just turns into multiplying by j omega. So now we have j omega a d. We have the same relationship between E and D and the capacitor voltage as before. But how do we write down that capacitor voltage in terms of in a phasor form? So here's how we do it. We know that little VC is equal to sine of omega t, which is equal to the real part of phasor form of VC times e to the j omega t. Now, e to the j omega t is equal to cosine, sorry, I'm going to write some things down. Real part of VC times cosine omega t plus j sine omega t. So if we just want to pick out the sign and have it have a positive sign in front, we don't want it to be negative, then what we need is for VC here to have a factor of minus j on it. Because if you multiply minus j by the cosine, you get minus j cosine, and when you take the real part, that'll go away. When you multiply minus j times j sine omega t, you get a plus 1 times sine omega t. So that means that VC in our situation, we're going to use minus j for. All right, so back to up here where we were doing the integral. ID, which we have just evaluated, is equal to j omega a, and in place of d, we're going to write epsilon VC, which is minus j v naught over d. So that's our expression. This stuff that I drew a box around in red is our expression for d. And remember, we got the time derivative just by multiplying by j omega. So that was a little bit easier, even though we had to do a discussion about how to figure out whether it should be minus j or plus j right there. Okay, so here's where phasor form really can help you. We also have to find out what the conduction current is. And to do that, we just use Ohm's law. We have VC again. So VC, whoops, I'm still writing in red. VC is minus j times v naught. And the conduction current is going to be equal to VC divided by the impedance of the capacitor, which is the impedance of a capacitor. I'm going to make a little bit more math space here. ZC equals minus j over omega c. Or it is 1 over j omega c, however you want to do that. So that means that IC is equal to j omega c VC. But remember that that C is equal to epsilon A over D. So then we have j omega epsilon A over D V naught. And then I'm going to substitute in the actual value that we have for VC, which is minus j V naught. Which, would you look at that, is the same as what we have for the displacement current. So let's take a minute to compare those. Displacement current right here, j omega epsilon A over D times minus j V naught. Conduction current over here, conduction current over here, j omega times epsilon A over D times minus j V naught. Same answer. If we wanted to get the conduction current in time domain, we could do that too. Conduction current is just going to be C dV dt, and here what we're doing is VC. So the capacitance again is epsilon A over D, and the time derivative of VC is going to be V naught omega cosine of omega t. You can see that we came out with a cosine when we worked in phasor form as well, because we've got a j multiplied by a minus j, and that's just going to give us positive 1. So if I convert IC to time domain, what I'm going to do is take the real part of, I'm going to get rid of those two j's by multiplying them by each other. So I'm taking the real part of epsilon A over D omega V naught e to the j omega t. Remembering again Euler's identity, e to the j omega t is equal to cosine omega t plus j sine omega t, and that means that when we take the real part of that, the sine goes away and we're left with only the cosine. So in that case, we get the same answer as we did for the time domain conduction current. And we would get the same answer if we did the same thing for the time domain displacement current. And there you go. That shows you how displacement current maintains charge continuity in situations where no actual current is flowing. And it's a good example of how to use phasors to solve this sorts of problems. Anytime you have sinusoidal signals, they're easier to deal with if you're using a phasor. So give it a shot next time.